Hey there, physics folks. In this video, we're going to review this uniform circular motion FRQ. This FRQ appeared on the AP Physics B test in 1999, in case you're looking, and it was question number 5. So what we have here is a coin of mass 0.005 kilograms is placed on a horizontal disc at a distance of 0.14 meters from the center as shown above. The disc rotates at a constant rate in a counterclockwise direction as seen from above. The coin does not slip, and the time it takes to make one revolution is 1.5 seconds, so that's going to be the period. Now, this is a typical situation where you have something moving on a turntable, a flat turntable, and friction is providing a centripetal force to hold this coin in moving in a circle. As we know, if something is going to move in circular motion, it requires a force to change its direction, and in this case that force is friction. Now, that's all good to know as you approach this problem, but you really want to make sure you read the question and carefully think about what the question is asking. So here we have a top view, and it says the figure shows the disc and coin as viewed from above. Draw and label the vectors. So we know a vector is an arrow that points in the direction, and the length represents magnitude. The vectors on the figure below to show the instantaneous acceleration and the linear velocity vectors for the coin when it's at the position shown. Okay, so as this coin is moving in a counterclockwise circle, it's going to it always has an acceleration, and it always has a velocity, and they want the linear velocity. So at any given time, sometimes we call the linear velocity the tangential velocity, so we're going to label this vector the tangential velocity, or v. You could say vt if you wanted to, it's not really necessary. And then they want to know what the acceleration is. Now, the acceleration of something moving on a circular path is, of course, the centripetal acceleration, and that is pointing towards the center of the circle. Now, the length of these vectors probably aren't that critical at this time. They just want to make sure that you know what the direction of the velocity and the acceleration respectively are. And clearly acceleration has to be towards the center, velocity has to be tangent to the circle. So that's what we would have for this first one. Be careful, because I know we've discussed forces, and you might be tempted to put the force of friction pointing inward, which is what holds it in the center. But it doesn't ask for forces, it asks for the acceleration and linear velocity. So that's what we would get for that. We'll go over the scoring rubrics from the College Board once we finish this whole test, or finish this whole problem, and we'll talk about how well we did. Okay? All right, the next one says, let's determine the linear speed of the coin. So that's the VT, the tangential speed or the linear speed going around the circle. Now, at any given time, speed, if we recall, the formula for speed is just distance over time. But when we're moving in a circle, we have a special distance and a special time. So the special distance would be the circumference as it moves around this circle in this circular path. And the formula for circumference is 2 pi times r. And the time that it takes to do that circumference or follow that distance is the period t, the time for one revolution. At this point, we can go ahead and plug and chug, so it's going to be 2 pi times the radius, and if we remember, the radius was 0.4 meters, or 0.14 meters, excuse me, from the center. And in the time that it takes for one revolution is 1.5 seconds, so that is going to be the period. And when we plug and chug, plug in some numbers, do the calculations, you're going to get 0.58643 meters per second. No naked numbers, don't forget your units. And of course, you'd probably round this to 0.59 meters per second. Okay? And so that's our answer for that one. The speed that it has is of course just the distance around, as we said, time divided by the period. But don't forget, you want to make sure you don't just plug numbers in and and calculate an answer, you really want to show your derivation or your concepts that you're showing your understanding. Clearly, this is an easy, relatively straightforward mathematics problem. So it's really important. The goal here for the College Board, I believe, is to get you to understand that you understand what speed is in a circle and how you can calculate it. So that's why it's important to show the derivation or start with an equation. Okay, cool. The next one says the rate of rotation of the disk is gradually increased and the coefficient of static friction between the coin and the disk is 0.5. Determine the linear speed, so that's this speed here, of the coin when it just begins to slip. Okay? Now, if we think about what's going to happen here, we know, and again, they didn't ask us for this, but that we know that it's friction holding this coin on its circular path. And as we increase the speed, of course, it's going to take more force to hold it in its circular path because, of course, that requires a greater acceleration with greater speed and therefore a greater force. Now, the first thing we always want to start with, anytime we're talking about forces, it's almost always a good bet to start with the sum of the forces equals ma, which, of course, is your second law statement. Now, to make sure we understand what's going on, we know that this second law is referring to circular motion, so we could also say that the sum of the forces is instead, or similarly, F equals mv squared over r, which of course is the centripetal force and centripetal with respect to centripetal acceleration. Now, what's holding this object in the center of the circle? Well, the only force that's causing this motion in the circle is the frictional force. Okay, so we might want to write down that the frictional force equals something, and so we could say that the frictional force is equal to mu mg. Of course, it's mu Fn, but Fn is mg because we have a horizontal disk or a horizontal platform, and we know that the frictional force is the centripetal force, and that is the only net force that acts. So we can effectively say that our second law statement says that the frictional force equals mv squared over r. Now we can see clearly that ff equals mv squared over r and ff equals mu mg. So the easiest thing to do here is to set these two forces equal to each other. So I'm going to say the force of friction, mu mg, is equal to mv squared over r, because that is the only force that acts centripetally. Notice that we have mass on both sides of the equation. The mass of the coin appears on both sides of the equation. And so we can say, quote, the mass cancels, or sometimes Mr. P from Flipping Physics says everybody brought mass to the party. And so we end up having a simplified expression that just says, let's keep with the purple here, mu g equals v squared over r. And when we're solving for, let's not forget, we're looking for the linear speed, so we want to solve this for speed. When we solve for speed, we're going to get v equals the square root of mu g r. And because this is a 1999 Physics B test, we're going to be plugging in numbers. In the newer tests, the AP Physics 1 test, we don't see a lot of quantitative measurements. But in this case, in this test, we are going to, so we'll go ahead and say the square root of what's mu, 0.5, no units on that, it's a pure ratio, 9.8 meters per second squared, the acceleration due to gravity, and of course the radius, which is 0.14, has not changed. Because we were looking for the critical speed at this radius when it just begins to slip, and that's when the friction force equals the centripetal force. And if we plug and chug and solve this, we should get a number close to 0.2825 meters per second, and we're probably going to round that to a couple of digits, 0.83 meters per second. Okay, and that's our speed. Now, anything above that speed, the coin will not remain in circular motion. Anything below that speed, it will remain in circular motion. Okay? All right, now, the last part of this question, and this was common with the AP Physics B test, was they'd have you go through some explanations, some calculations, and then sort of apply your knowledge to a new situation. So it says the experiment in part C repeated. If the experiment in part C, the increasing the speed until it slips. Repeated with a second identical coin glued with massless glue, so the glue doesn't add any mass, to the top of the first coin. How would this affect the answer to part C? Explain your reasoning. Now, I went ahead and bolded this when I created this document. The original test document wasn't bolded, but you should always remember when a question asks you to explain your reasoning, you really want to make sure that you do a succinct yet thorough job of explaining the concepts. Now let's think about what's going on here. Let's take a look at the side view of this coin, or this turntable. So if this is our turntable and it's spinning around, and we have the first coin here sitting on it, and as it spins around, we know that there's a frictional force pulling it inward, FF, and we know, of course, that's mv squared over r, because that's the only coin, or the only force. If we add what they're asking is if we add a second coin on top of it, what will happen to this experiment that we conducted up here to find the critical speed? Well, if we think about it, the only thing that's changed here, and we say with massless glue, why? Because the only thing that changed is the added mass of the coin. Even if it was glue with mass or some other thing, notice that the equation that we found, or the derivation that we found for speed, does not include the mass. Okay, so clearly you could add as many coins on top of here as you wanted, and it would not change the critical speed at which this first coin at the bottom would start to slip on the surface. Now the reason for that is of course, as we increase the mass, it certainly increases the centripetal force required to keep that coin on the circle, or keep that mass on the circle. However, the force that keeps it on the circle is a frictional force, and you'll see that the force that is required to create a circular motion is derived from the frictional force, and both those depend on the mass of the object. And when we set those two equal to each other, you can see the mass increases, or is the same on both sides of the equation. So if we double the mass, we're going to have double the mass here, and that won't, of course, change any of these relationships. So the answer to the question is there would be no change, and you might refer to part C up here, no change in critical speed. And the explanation is it probably could be as simple as the m's cancel, or you could say something like mass is not a factor, and refer to your equation up above. Okay, so let's take a look very quickly at how we did, so to speak. Okay, so let's see. The first part of this, and these are the scoring guidelines from the 1999 physics test, and it's a little faint here, but for the first part, they said for any properly labeled vector for velocity pointing upward, and any properly labeled horizontal vector pointing to the left, and of course that's what we have. The 2 points for part B were deriving the expression for the linear speed, which is of course the circumference over the period. Plug and chug, and you should get 0.6. We got 0.59, which is close enough. The next part was talked about a little bit the critical speed down here, and so we have the centripetal force equals the frictional force. The expanded expression of that, the v equals root mu rg, which is of course the solution to that expression. Notice how they give you the points. You needed a correct expression for the centripetal force, so that's the mv squared over r. A correct expression for the frictional force, that's mu mg. Again, I think it's probably a good idea to express those separately. For equating the centripetal force to the frictional force, so saying that the two are equal, and then for the correct answer, plugging and chugging. Okay. For the last part, which was what happens when you add the second coin, if you'll notice here, it says for indicating there's no change, which as we proved, because the mass appears on both sides, and it says for any reasonable explanation, including saying the mass is canceled, which is kind of an informal way of saying it. But they would accept that because, of course, they're expecting you to have derived this expression up here prior to that. Now, notice here it says no points were awarded for any explanation if it was without a statement of no change. So it's really important, again, like I said, to do both things, right? Answer the question, what will happen, okay, or how will this affect the answer? It won't. And then explain. So those are two things. So you want to make sure you do two parts of your answer. Okay, that's it for this one. The links to a document similar to this and the College Board solutions will also be in the description. Thanks very much.